All right, let's start. So today, as promised, I'm going to show you the Witten's volume formula for the volumes of moduli spaces. Of course, well, to simplify things, we only look at some kind of easy cases, but still, I think that's a beautiful formula. So for today, or at least for the next few minutes, we're going to fix G to be compact and simply connected. And for sigma, let me choose the surface of genus G, and there will be only one boundary component. And let me choose mu in the while alcove such that the exponential of mu equal to z is a central element. So now, what's this Witten's formula? Well, we're supposed to compute the volume of the top stratum of the moduli space M sigma G mu with respect to the T-bar symplectic form. Now, well, what is the answer? First of all, there is a number of central elements of G. So the number or the order of the center. Then there is a volume of G to the power 2G minus 2. I'll say some words about this volume in a second. And then, well, there is this interesting sum over lambda, the dominant weights, or let's say lambda irreducible representations of G. And here there are those interesting denominators. So the dimensions of those irreducible representations to the power 2G minus 1, and here there will be a character of this representation computed at the central element Z. So you see, this is kind of, at least at first sight, this is a interesting and complicated looking formula. So let me make some comments about it. Well, first of all, for the volume of G, remember that the Lie algebra carries this invariant scalar product, and it induces a Riemannian metric on G. So that's the volume with respect to this Riemannian metric, with respect to the scalar product on G. So that's one thing. Perhaps here I should make a comment that the formula is valid for the genus is at least equal to 2. Remember that actually that's where the generic dimensions start. For G equal to 0 is anyway, it's a different story, and even G equal 1. That's not clear. Depends on Z perhaps whether it's good or not. Now perhaps the second comment, if we put z equal to the group unit. So then actually we go back to the moduli space of the closed surface, sigma of genus G, and this sigma is empty. Well, maybe the third comment, we were always sticking to the situation of a trivial G bundle over the last 3 lectures. But in fact here just one small comment. So if z is not equal to 1, then this corresponds to moduli for non-trivial bundles, but then for which group? For the group G tilde, where G tilde, for instance, is a quotient of G by its center. Or you can take, if the center is big, you can in principle also think of smaller quotients, but then this would depend on the choice of the central element. Now, perhaps some more comments about it. Let's write this formula in the example of G equal to SU2. So the volume of M, and here we have sigma and then SU2, and then, well, to simplify things, let me put this element mu equal to 0, which means that z is just equal to the group unit. So what would we get then? So there will be a factor of 2 for the number of central elements of SU2, and then there will be a volume of SU2 to the power 2g minus 2, and then, well, there will be a sum over irreducible representations of SU2, but we know that there is exactly 1 in each dimension starting from 1, so this will be sum from 1 to infinity. And, well, if I put z equal to the group unit, this guy also becomes a dimension. So there would be a partial cancellation here. So in the denominator, I will have a dimension to the power 2g minus 2. So it will be here 1 over n to the power 2g minus 2. So this guy is just the zeta value at the point 2g minus 2. So there are kind of interesting rational numbers which come up here. It's expressed, in particular, it's expressed in terms of Bernoulli numbers. So why do I bring to your attention the SU2 case? Because in this SU2 case, perhaps for me, it's easier to state that there are various generalizations or various higher analogs, or one can say, of this formula. So, in fact, well, I bring this formula to your attention as a simplest and typical example of global results about the moduli space, but there are other results. For instance, let me state for SU2 the famous Verlinde formula. So there are Verlinde numbers which in some sense generalize volumes. So Verlinde of sigma and SU2, and there will be an integer that I will comment on in a second. So it's given by k plus 2 over 2 to the power g minus 1, and here again there will be a sum over n, but the sum will be finite from 1 to k plus 1, and here there will be 1 over sine. Well, it's easy to make a mistake. So pi n over k plus 2, and this sine function will be to the power 2g minus 2. So these are so-called, so that's the index of the level k quantization of m sigma SU2, and famously those numbers, unless I made a mistake in the coefficient somewhere, they're all integers, right? That's not at all obvious except for the case of g equal 1. For the case of g equal 1, this is a sum of ones. But for the other cases, this is highly non-trivial statement that those numbers are integers. And so this level k, that's the power of the pre-quantum line bundle over the moduli space. When k becomes big, the asymptotics of those numbers, the leading term in the asymptotics will be controlled by the volume. So you can in principle derive this volume formula if you know the Verlinde formula. And you see it's also of a similar type. So here I wanted to draw another arrow, but the Verlinde formula took the whole blackboard. I won't write another arrow, but for the case of G equal to SL to C. Obviously, then the moduli spaces are non-compact. It's difficult to speak about volumes, but very brave physicists can do it. So there is a Moore-Nekrasov-Shatashvili formula, which is still kind of, I think, I'm not sure. I heard talks by Hausel and Zenisch about the proofs of this formula, but I checked yesterday evening. There is still nothing on the archive. So, but the essence is that they introduce an extra S1. So then the moduli space become a hyperkähler manifold, and there is an extra S1 action, which allows, in a sense, in a physics words, regularize the infinite volume. In mathematical words, may understand it in terms of equivariant homology. So then even some infinite integrals may converge if you introduce in the equivariant homology some exponential factors which make them converge. So the interesting part is, see here there are integers n. So, and those integers are replaced in the Moore-Nekrasov-Shatashvili formula by the solutions of transcendental beta equations. Well, those of you who heard of integrable systems, they might have heard of beta equations. So this is a system of transcendental equations, and their solutions, if you send some parameter to 0, they will tend to integers, but then otherwise these are some complicated numbers. Of course, it's not kind of here you replace them and you also do some other small modifications with the formula. But still, so there are various generalizations of this formula. And okay, one perhaps open question to formulate in this context: is there some universal, well, we can call it volume, but okay, global quantity type formula? For moduli, like the minimal condition would be take in those three cases, or at least two of them. I don't quite know how high you put the target. So right now.
Could you say a bit more about this? I don't understand the question really. What are you asking?
Okay. You see, I don't quite know, but one possibility would be as follows. but this is my speculation. So now we're looking at solutions of various equations in the group. For instance, here we have solutions of this equation, and we look at those solutions, for instance, in a compact group, or at solutions of this equation in SL2C, or in some complex groups. My approach, for instance, would be, let's consider solutions in a free group, and let's try to define some structure, some volume type structure universally, which would use, for instance, free group. Or perhaps one other idea, but this comes from my background, it might be completely wrong. Let's take a pro-unipotent completion, which means let's allow the logarithms of the generators, and let's try to build. So this would give already a lot more structure. For instance, here there is immediately some field, for instance, of characteristic 0 that we throw in, and let's try to define this volume type object in terms of this free Lie algebra. Okay, this might be a wrong approach. Perhaps it goes too far, in the sense that, well, okay, here we have some groups, but still they look the same, almost kind of a bit similar. Some of them compact, some of them non-compact. Here we do something in homology, here we do something in case theory. Okay, here I really lift it quite fast, saying it's just a free group or free Lie algebra. Okay, maybe one should stop somewhere before that. Even though one should say that for some problems this approach does work. So it leads to various deep notions like the Grothendieck-Teichmüller group and deep questions in number theory, which are perhaps related also to the values that we are getting here. So okay, but this is my wild speculation. It looks strange that we have different theories where people obtain those formulas struggling and with different methods, and still the structure of the formulas look relatively similar, even though there are some huge modifications, like these beta equations instead of integers, or here we have those trigonometric functions instead of rational functions. But still, maybe there is a universal.
Are you implying that the formula can also be understood as a volume?
No, but I mean, in some sense, it's a proper case theoretic replacement, right? It's an analogy, right? There is case theoretically, the index is what replaces the volume on the symplectic side. So perhaps here in the completely non-commutative context there is a universal functor which would specify to these two formulas. As I say, this I present as a very, very wild speculation. I have no clue of how I would do it. But at least we know that in somewhat similar problems, like on the Grothendieck-Teichmüller side, still for quantization of bialgebras and so on, this approach does work. So who knows, maybe it works here as well. Okay, now, right, so that's the big formula I wanted to present to you in this lecture and actually in this mini course. Now what should we do for the rest of this lecture? My idea is to present to you a kind of sketch of one of the proofs for this formula. Of course, now the formula is complicated and it looks difficult. I split my sketch of the proof into 8 steps. So we'll see how far we can go along this path. But maybe now just one word of motivation, the technical motivation. So let's denote by phi the commutator map which maps a 2G tuple of elements into a product of group commutators. So then the moduli space, at least for a closed surface, it looks like the inverse, the fiber of the group unit, the inverse image of 1 divided by the group action. For quite a while, people saw that this looks very similar to a Hamiltonian reduction, to the picture that we saw in the first lecture. Unfortunately, this idea doesn't, or fortunately, this idea doesn't work directly. Why is that? So then the space from which we would reduce would be the space g to the power 2g. But then this cannot be a Hamiltonian space, because g to g is not symplectic. So that's because h2 of g is 0. If you take g compact simply connected, which means that it's, in particular, it is semi-simple, so the h2 has to vanish. And then g is compact, so there is no place in cohomology for symplectic form to live in. So step 0 is to extend the definition of Hamiltonian spaces such that we can acquire spaces with vanishing cohomology, compact spaces with vanishing cohomology. Okay, so step 0. So this is a definition of so-called group-valued moment maps. So as before, for ordinary moment maps, we start with a triple, a manifold, a two-form, and the map which we suggestively call phi from M, and now it goes to the group G. As before, we assume there is a pairing, there is a scalar product on the Lie algebra. So that's an important ingredient. So that's an invariant scalar product on G. Well, so this triple is a G-valued Hamiltonian space if, well, the following conditions are satisfied, and this is parallel to what we did before. So G acts on M. Well, it's parallel, but also it's a little bit different, and we had this exercise that we did yesterday. So d omega will not be 0. So it's not going to be symplectic as we said, but instead this will be a pullback of the Cartan 3 form. So remember, there was this Cartan 3 form on the group. So we now pull it back, and d omega is supposed to be the pullback of this Cartan 3 form. Now also, omega will have a kernel. We'll see that it will create some problems for us in the immediate future. So this kernel consists of values of fundamental vector fields which satisfy the following funny equation. So the adjoint of the value of the moment map on X is equal to minus X. So it's an eigenvector with eigenvalue minus 1. I must say that some considerable effort was invested into understanding of this condition, and by now I think it's very well understood. So, but I I'm perhaps not very competent to speak about the more recent studies in this direction. So so at the moment it looks a bit strange, this definition, but let me continue. So the moment map condition, remember the moment map condition should say what is the contraction of the fundamental vector field with omega. And here again, if you looked at the exercise, there was this interesting combination. So 1/2 of the scalar product of x with the sum of the left and right invariant Maurer-Cartan forms. Right? So we saw it in the exercise, and now it comes up in the moment map condition. Finally, fourth condition, phi m to g is equivariant for g action on g by conjugation. So, well, of course, once one gives a strange definition, then one has to justify why it's a useful definition. So, it turns out that basically all the good features of the ordinary definition of moment maps, they carry over to this strange definition. So I will show you some of them, because for the others we probably wouldn't have time. But in particular, like step 1, one important question for us whether reduction works, right? Because we were kind of focused on reduction in this mini course and also in the other mini courses. So the reduction actually works 100%. That is, the quotient of m by g is just Poisson without any corrections. And the reduced space, let me write it for the group unit. One can also do it for other values, but well, since we don't have that much time and we are focused on the group unit, let me do it for the group unit. So the reduced space is symplectic. So all those pathologies of the two form, they go away once you proceed with the reduction. And reduction is defined exactly in the same way as we did before. So you take a fiber of the moment map, you embed it into the manifold, and you project to the reduced space, and the form, the pullback of the form on the reduced space is equal to the pullback of the two form on M. So this guy is not closed and is degenerate, and this guy is symplectic. It's closed and non-degenerate. Of course, there is no contradiction, but there is something to prove. Right. So that's step 1. Now, for computing volumes, what will be handy for us, and how volumes of reduced spaces are computed actually in the ordinary Hamiltonian case, one uses the Liouville form. So we need something like a Liouville form on this space. Well, we have a little bit of a problem here, because the form omega is degenerate, right? So if we simply take so Liouville volume. Well, so if we simply try to define this Liouville form as omega to the power dimension of m over 2 over dimension m over 2 factorial. So here we would fail, because the because there would be a kernel of omega somewhere, and the place where we have a kernel, this volume form would vanish. Now, in principle, there is a whole beautiful story how to get an expression of this guy from various considerations. Like one of them is a Clifford algebra calculus, or another one is a theory of pure spinors. But for today's purposes, let me just give you a formula. This formula is a little bit wrong, but I hope it's okay, right? It's a boundary effect of the mini course. Now you will tell me why is it wrong. So in fact, it's sufficient to correct it by a coefficient which is 1 over 1 plus adjoint phi operator over 2 determinant, and we should take a square root of it. So how does it look for you, this formula? And what's wrong about it? Well, you immediately see what's wrong. See, here we were speaking about the kernel of this adjoint phi plus 1 operator. And here we are dividing by the determinant of this operator. So, see, the point is, in general, this guy, the top degree of omega vanishes somewhere. It vanishes on the locus where this adjoint phi plus 1 has a kernel. Now this guy also vanishes at the same place. So it's like a rational function. So something which vanishes here divided by something which vanishes at the same place. Now it might be that the singularity cancels out. And that's the case. It always works with the exception of the cases where, for instance, you can imagine we can imagine those group-valued Hamiltonian spaces where there is a kernel everywhere. So this also might happen. And then you have to replace this definition with some more proper definition. We're not going to meet those spaces today. That's why let me cheat a little bit and give you a slightly non-general formula. So it turns out this is a volume form, right? So that's also a kind of small result.
It may not be totally clear even why the dimension of M is even.
Yeah, that's right. Exactly. But I think in this context it's going to be right. Right, maybe a good remark. Right. Okay. Now, remember we had in the Hamiltonian context, we had a theory for products. So we could take two Hamiltonian spaces and take a product. So number 3, products. So suppose we have mi, omega I, phi I from M to G, G-valued Hamiltonian spaces. So then we want to have the space M1 cross M2 with some form to be discussed. And well, for the moment map, we probably know what we want. If we take a pair of points M1, M2, then we want phi 1 of M1 times phi 2 of M2. You see, interestingly, before we had a sum of those moment maps. Now we replace it with a group multiplication. Well, here, of course, we imagine that as before, you can compare to what was going on in the first class. So we can imagine that we put here the sum of two forms. Unfortunately, it doesn't, or fortunately, it doesn't work this way. So there is an extra term. Interestingly enough, this extra term we can learn if we read, as usual, the physics literature. It was first discovered by the physicists Polakov and Wigman in their studies of conformal field theory. But okay, for us it's just I knew where to look for it. But well, let me write it down. Actually, it's a differential form. Well, let me give you two writings, and not very scientific writing as I prefer, and then the scientific writing. So it is built of the Maurer-Cartan forms produced from the two moment maps. So this is 1/2 the pairing, and this is the pullback under phi 1 of the left invariant, and then the pullback by F2 of the right invariant Maurer-Cartan forms. You see, I first write it this way, and then I read what's the proper writing is. Now, let me state it here, and then leave the blackboard. An important theorem. Well, the
This is a theorem for what?
so this plus this plus this. Sorry. Yeah, maybe I should. Yeah, I started writing. Yeah. So that's the.
Do you mean phi 2 star also in the
Yeah, right. Okay. So you see, something funny happens with those two forms. But here, in this generalized or whatever group values theory, you always have to ask the right question. And the answer to the right question is always positive. That's a kind of nice feature. Now, well, as I said, we're going to be interested in the volume forms. And you may ask, what's the volume form on the combined space? And it turns out that for the volume forms, that's simply the wedge product. See, there is something complicated which is going with the moment maps. There is something which is really complicated which is going with the two forms, even though there is some beautiful supergeometric interpretation in terms of supergroups. There is a beautiful explanation of this law. But then with the volume forms or with the Liouville forms, they just multiply, as in the case of ordinary Hamiltonian or ordinary symplectic spaces. Okay, what's the next step? What can probably I should sacrifice something here. I should keep the formula though, right? I cannot erase the formula. Now this is an important moment because we are in Utrecht. So and I think it was already implicit in the last Ruiz lecture. So the next step, 1, 2, 3, 4, right? 4. Duistermaat-Heckman measures. So of course the influence of Duistermaat on all this development of the moment maps theory and of other related fields was enormous, and so this is inspired by his approach. So what one can do once one has a compact manifold equipped with a moment map or with a group valued moment map as it is here, one can define the Dustermott-Heckman distribution, let me denote it by curly m, and this is simply a fiber integral of the Liouville form along the fibers of the moment map. So you have this map from one compact manifold to the other, and you just integrate the Liouville measure along the fibers to induce a measure on the target of your space. So in general, what we get is a distribution on the group. Because of the equivariance properties, this distribution is conjugation invariant. Now, there is the following simple statement, and if you think a little bit about it, well, fact. So that's not a difficult statement, and it's similar to what happens in the ordinary moment maps theorem. So the volume of the reduced space, let's say the reduced space at the group unit, is given by the following formula. Let me write it down and then let me comment on it. So it is some number k divided by the volume of G, and here the quotient of M by D volume of G computed at the group unit. So let me explain the notation of what's going on here. For the volume of G, we already said, right? That's the volume with respect to the scalar product. Now, what is this M divided by D volume? So this is a distribution, but we hope that this is a kind of nice distribution. So we imagine that this M is a product of the Haar measure on G times some relatively nice function. So this is not always true, but okay, let's pretend this is true. So this is a kind of Redon derivative, Redon-Nikodym derivative of this. So assuming that this is an absolutely so that the measure M is absolutely continuous with respect to the Haar measure. So this is a Redon-Nikodym derivative. So assume that it gives you a nice function. Then we evaluate this function, in this case, at the group unit. That's basically, of course, that's the same place where we want to evaluate our volume. And K, finally K, is the number of points in the so-called principal stabilizer of the G action. Well, that I'll tell you in a second how it works. But you see, we always assume that the action is free. Unfortunately, in our main example, this will not be quite the case, because G acts on itself by conjugations. This means that the center doesn't act, right? When you conjugate, central elements don't act. So there will be some stabilizer after all. So this principal stabilizer, that's basically the stabilizer which you have in the even on the top degree stratum. And that's the one which I have here. I don't state all the assumptions very clearly. Now, well, you can roughly imagine why something like this might be true. What is this Liouville measure after all? The Liouville measure is produced from the two form on the reduced space, and then the moment map condition tells you something about the interaction between the coordinates along the fibers and coordinates along which parameterize the neighborhood of the group unit in G. So the fibers in this case, they are isomorphic to the group. So here you have this volume of the group, And the normalization here is chosen in such a way that you don't get any coefficient corresponding to the coordinates in the on the neighborhood of the group unit. So this is a simple fact which kind of uses the local models for symplectic forms near the reduced near the level sets of the moment map. Right. So this was, well, how is it going? Well, we're still on time. So this was step 4. Now I think 3 more steps. Well, step 5. Now what can I sacrifice? Would it be okay if I sacrifice the Liouville forms for a moment? Step 5. Now, well, finally I'll give you an example of a group-valued Hamiltonian space. Well, and this example is called the double. So I take the product of the group with itself, and that's a kind of counterpart of the cotangent bundle of the group. Right? That's a very important symplectic space which carries a moment map. It showed up in several mini-courses already. So if you want to develop kind of moment maps theory, we need a counterpart of it, and in this case this is G cross G. Now I will be acting on it not with 1 copy of the group but with 2 copies. And the action will be as follows. It will be let's say here GH is mapping A and B into GA H minus 1 HB B minus 1. And well, usually it's not so easy to write those quasi-symplectic forms. But here there is a beautiful expression for this quasi-symplectic form, and it's equal to 1/2 A minus 1 dA dB B minus 1 minus 1/2 B minus 1 dB dA A minus 1. Well, I'm not sure. I guess I'm not allowed to give exercises, right? Because that's the last lecture. Still. So several things. Check that it's okay, meaning that it satisfies the properties announced in the definition. Now, what is this form for G equal to S1? This is, of course, not the case that we are usually considering here. Our simplest example is usually SU2, but still, what is it in the case of S1, and what those definitions give you in this case? That's an interesting and easy exercise. And finally, in the lecture notes that I distributed, there was some part on the computation of symplectic forms on the moduli space. So this part is not coming up in the lectures. So it's in the lecture 3. But and in those lecture notes, this form comes up from the calculations on the moduli space. So I suggest you to compare to lecture notes and see how, in what context it comes up in the lecture notes. Right. And finally, I should have told you what was the moment map. So the moment map also takes values in G cross G. And suggestively, it is AB and then A minus 1, B minus 1. You see, it's not a group commutator. But of course, remember, we had this, just in this step 3, we had this possibility to multiply the moment maps. So if we multiply them, and of course if we add this ugly term, that's why I don't write it here, you would get a moment map which will be exactly AB, A minus 1, B minus 1. Now, well, we're approaching the end, step 6. Step 6. Theorem. So let's consider G copies of this double. Well, we have two G moment maps, two copies of G for each of them, and let's multiply all of them. Of course, when we multiply all of them, this will produce a lot of extra terms in the 2 form. So let's call this manifold M. Of course, it's isomorphic to G to the power 2G. And let's call this composed map the map phi. Now, well, this is a map as we wanted from the very beginning. AGBG maps to the product of commutators. And of course, there is a 2 form which comes from those constructions. So the theorem says that the reduced space at the group unit is isomorphic as a symplectic space to the moduli space of flat connections on a closed surface of genus G. Well, of course, this was already suggestive that we should take a fiber of the moment map, then we should divide by G, so we do obtain this space, but we also obtain the correct symplectic structure. Now I guess we should sacrifice the definition. So we may wonder what is the volume, what is the Liouville volume on this space. So the Liouville volume on G to the power 2G, let's say fact, and it turns out that this is simply a product of Haar measures on all the 2G copies. So that's as simple as that. As I say, whenever you ask the right question, the answer is always simple and positive. Right. Well, now we need to determine this Ducermat-Heckman distribution, and we need to know what is the value of this function at the group unit. In fact, the efficient way to do it is as follows. Let me perhaps switch again to this blackboard. So this f of g, because of the g invariance, is a class function. So the function which has a property that f of the conjugated argument is equal to f of the original argument. So that's why one can actually use the theory of characters to represent it. So we can write, so this f of g, this is Radon Nicodim derivative, and we can write the Fourier transform formula for it in terms of characters of irreducible representations. So here would be chi of lambda, so the pairing of the integration between our measure and chi of lambda, and here chi of lambda of G inverse. So basically what we need to compute in the end are those coefficients. We need to take this measure and compute the Fourier coefficients with respect to irreducible characters. Now, so we have a commutator map. So those 2G tuple goes to the product of commutators, and we have a Haar measure on each copy of the group. So we need to compute the image and compute its Fourier coefficients. So you see, for those of you who were at the exercise session in the morning, we did exactly this for a finite group. And you know that for all calculations with characters, finite groups and compact groups, that's roughly the same story. So this is a computation in the theory of characters. Let me just give you the answer. So you take the push forward of this measure and you evaluate it on chi lambda. So the calculation is exactly the same as in the morning at the exercise session, and the result is the volume of G, not to make a mistake, to the power 2G over the dimension of V lambda to the power 2G minus 1. So that's a beautiful calculation. If you never seen it, I encourage you to do it unless you were at the exercise session and you saw how it actually works. Now perhaps before concluding, the one last remark about the relation between what we are doing here and topology of surfaces. You see, actually one can draw a picture of how we glue a surface from pieces here. And the dictionary is as follows. So a topological interpretation. So to a double, we associate a cylinder. So we start by taking G cylinders and the corresponding moduli spaces. And then to the product, we associate gluing of the pair of pens. So this a sphere with 3 holes. So for instance here, we're attaching this pair of pens. Well, here my pens don't want to glue very smoothly. So we're attaching those pairs of pens to each of the cylinders. So that's when I'm multiplying these two maps. And then I continue attaching pairs of pens. See? Well, so on. For instance, here. Imagine that we had just 3 of them. So then, one more pair of pens. And that's what we got. So this construction corresponds to gluing a surface of genus G. You see here those G holes, and with one boundary component, that this remaining pen, which is not paired, which is not glued to anything. Right. So to conclude, we now see what happens, how this formula comes about. So there is this K. That's the number of elements in the center of G. That comes from this K. Now this volume comes from many sources. So there is a volume to the power 2g in the Fourier coefficient. There is 1 over volume in the Fourier transform, and there is 1 over volume in the Dustermatt-Heckman formula. So that's how we got to g minus 2 here. Now, of course, the sum of irreducible representations comes from the Fourier transform. So now this dimension to the power 2g minus 1 comes from here. And finally, the character comes from here. So that's what I get. So you see, sorry for kind of rushing through it, but just to show you one interesting approach which gives you this formula. In fact, it's useful for proving some of the other formulas that I showed to you before. I would like to conclude, if I still have maybe 2 or 3 minutes, with a small advertisement of some of the lectures in the conference, because it was supposed to be in some way preparation for the conference. Let me just, well, of course, perhaps this gives an unfair advantage to some of the conference talks. But there are some conference talks which are directly related to the moduli of flat connections, and let me just try to say in 2 words, to advertise in 2 words what they're doing. So directly related to the moduli, so moduli related. Well, so there is a talk of Boch, and Boch, as far as I understand, he's doing something like this. Remember, in the exercise 4 on the first problem set, there was this interesting flat connection, sum over simple poles at some points times dz. So this is in fact, roughly speaking, the same, or this is a different expression for the picture that we were drawing for a sphere with some holes. In fact, you can try to shrink those holes, but then there will be still some marked points at the tips. So those marked points, that's where you have poles. Now, so that's the classical story. What Boch is trying to do, he's trying to look at something of the sort. There is a pole, the first order pole, but there is also a second order pole and possibly higher order poles. So the Atiyah-Bott formula still gives you some nice symplectic form on whatever is the moduli space when you go here. The interesting part of it, I was telling you that the moduli space is completely described in terms of holonomics, in terms of the map of pi1 to your group. But here it's no longer true, because those are irregular singularities. And those irregular singularities in general, they start cutting your surface into so-called Stokes domains. So these solutions in general do not exist everywhere, or you cannot go around with the same solution and say what is a holonomic. So then you will have to go between different domains, and here you will have well-defined holonomics, so-called Stokes data. So those Stokes data, they do carry symplectic and Poisson structures related to Poisson-Lie groups, which showed up in the lecture series by Henrique. So that's, I think, some kind of very advanced generalization of it. That's what Boch gonna speak about. Now there is another talk about moduli by Leblanc, And well, I haven't found his paper about it on the web, but he's saying it's a continuation of some work with Severa. So what Severa is doing is something like this. In Henrique's talk, you saw those Drinfeld doubles. So when you build quadratic Lie algebras from the sum of a Lie algebra and its dual. So they are taking it very seriously, and so they are taking surfaces perhaps with boundary, and they try to put boundary conditions on those boundaries which are different from what we were discussing. So they are saying, let the connection, for instance, on this piece take values in only half of the Lie algebra, and in this piece perhaps in some other half. And well, things like that. So this also leads to Poisson Lie groups, so some kind of colored Moduli spaces and Poisson Lie groups. Well, finally, there is a talk which is, or there will be a talk which is intimately related to the Moduli spaces, but there I'm not sure I'm very competent to tell you how it's going to be. So that's a talk by Gukov, and he's looking at the Berlinde formula for the surface sigma and the group G, and he's relating some parts of this Berlinde formula to the Moduli space on the surface sigma and the Langlands dual group, the group corresponding to the dual root system. So there. So that's a different kind of duality, not like a Poisson Lie duality here. So another deep duality in group theory, and apparently it shows up in coefficients in Berlinde numbers. But there, okay, I just tell you what formally is speaking he's writing in his abstract. There, I don't quite know what it is. Okay, so those Moduli problems are related to other topics and actually surprisingly well represented in the conference. So, well, I think that's probably it.